Howdy! So, this is the video on all the identities for trigonometry. I'm going to run through all of them. I'm going to tell you why they all work the way they do. And then we're going to run through some examples on how to use them to simplify things or to prove that things are true. So there's 6 identities that we've covered in class. Here's one, cofunction identity. We know that if that's a 90-degree angle, and this is A, and this is B, then this would be C. We also know that the opposite side would be B and A and C respectively. And the thing is that if I had the sine of, let's say, A, we would know that sine is opposite over hypotenuse. And we'd look at angle A and we'd say the opposite side is A and the hypotenuse is C. So this would equal A over C. But if we switch to the cosine and we switch from angle A to angle B, then angle B has a different opposite side and a different adjacent side. So this is adjacent over hypotenuse. And from angle B, the adjacent side is still side A, and the hypotenuse hasn't changed. So those are the same. So what's happening here is in a right triangle, if you switch from one acute angle to the other, the side that's adjacent and the side that's opposite switch places because it's relative to position. And so what that tells us is that whenever you have 2 angles that add up to 90 degrees, the sine of one of those angles will equal the cosine of the other. And this is why the trig functions are named as they are, sine and cosine, tangent and cotangent, secant and cosecant. So, that would mean that the sine of an angle would equal the cosine of 90 minus that angle, 90 minus that angle, and vice versa. So the sine of 15 equals the cosine of 75 because they add up to 90 degrees. Tangent of an angle would equal cotangent of 90 minus that angle. And if you wanted to think about it in radians, it would be pi over 2 minus that angle. Secant of an angle equals cosecant of 90 minus that angle. So as long as the angles in question add up to 90 degrees, the cofunctions will be equal. Onward, second thing, periodic identities. Periodic identities are really easy to understand. They have to do a lot with the graph of the functions. So let's say I've got, but also they have to do with this mysterious shape, the circle. If I take this angle here, whatever that angle is, well, we know how to make coterminal angles. It's very simple. You just go in a circle from here, and you go around. And you go around 2 pi. And so the sine of any angle will equal the sine of that angle plus any multiple of 2 pi because they're coterminal angles. It makes total sense. You're just going in a circle. The cosine of an angle will equal the cosine of that angle plus 2 pi. Now here's the tricky one. It's not really tricky, it's just a little different. And it's the tangent of an angle equals the tangent of that angle plus pi. And the reason, not 2 pi, but pi, the reason has to do with the graph. So I'm going to bring up here, if I can find my mouse, I'm going to bring up sine of x. Now we can see sine of x repeats every 2 pi, every time around the circle. But if I put on tangent of x repeats not every time around the circle, but really every half a circle. From here to here is half a circle. So that's only pi. So the period of the tangent graph is pi. And as such, the whole pattern repeats every pi times around the circle, which is, half a circle. And so the periodic identity for this one is not 2 pi, it's just pi. Okay, onward. Reciprocal identities. These you should know already. It's very simple. It's that if the sine of an angle is y over r, and the cosecant of an angle is r over y, then sine is going to equal 1 over cosecant. Because if this is r over y, and you guys who are so good at fractions will know that if I'm dividing by a fraction, I'd have to flip and multiply. So I would take 1 and I would flip r over y to y over r and multiply it, and of course it'd equal y over r. So sine is 1 over cosecant. Also cosecant is 1 over sine, because that's how reciprocals work. It's just flipping upside down. Cosine. We know that the cosine of an angle is the reciprocal is secant. So cosine equals 1 over secant. You know, secant equals 1 over cosine. And tangent. Tangent is 1 over cotangent because they are reciprocals. Cotangent is 1 over tangent. Super useful. Quotient identities. Quotient identities also super useful. I'm going to give you two. There's bunches that we could make. But I'm going to give you the two big ones because everything can be derived from that. Tangent of an angle equals the sine of an angle over the cosine of an angle. And the reason this is so, and here's the thing, whenever you're trying to explain why things are true, it always goes back to meaning, and meaning is inherently definition. Tangent, by definition, is y over r. Sine, by definition, wrong. Tangent, by definition, is y over x. Sine, by definition, is y over r. Cosine, by definition, is x over r. Well, again, if you have a fraction divided by a fraction, would you not flip and multiply? So if I take y over r and I divide it by x over r, that's the same as multiplying it by r over x. Well, don't these r's cancel out? So that gives you y over x. So you can see this is exactly why the tangent of any angle equals the sine of that angle divided by the cosine of that angle. And because you're super brilliant and you know that cotangent is the reciprocal of tangent, and you know that reciprocal means just flip over a fraction, you would know that cotangent must be cosine over sine. And we could derive it the same way if we wanted to. Great, those are quotient identities. Onward. Negative angle identities. This one's a little trickier. But if you think it through, and if you go slow, it's not so bad. Here's a circle. It's a circle on a coordinate plane. Let's say that I have this angle. That angle makes this triangle. And I could pretend that the sides are something convenient. Like, let's say, 3, 4, and 5. So the question is, how does the sine of that angle compare with the sine of a negative angle? They're negative angle identities. So sine of a negative angle. Well, we know, like, does it equal the sine of the angle? Are they the same? Well, the sine of this angle would be y over r. Would that not be 3/5? Yes, it would. You're nodding and smiling at home. But the sine of a negative angle, you got to think of what a negative angle means. It means to rotate in the other direction. So if I take the same angle, but I rotate it down here, well, what happens? 4 stays 4 and 5 stays 5. But this is now a negative y value. This is now a negative 3. And so since sine is y over r, this is negative 3 over 5. These are not equal. But they would be equal if that was negative. And so, the negative angle identity is that the sine of a negative angle equals negative sine of that angle. Does it work with cosine? Well, let's think about it. Cosine of a negative angle would be that red one. And that cosine is 4/5. Because the x value is still 4, still positive, And the y value is always positive, the r value is always positive because it's the radius of the circle. That's a distance. So this actually equals exactly the same thing as the cosine of the angle. In other words, the cosine of the blue triangle and the cosine of the red triangle are exactly the same. And the reason that's true is because whether you rotate clockwise or counterclockwise, I always get those mixed up, but up or down, the x value stays the same sign, S-I-G-N, the same positive or negative. And the same thing would be true if we were in a different place. Let's say that we had, I don't know, purple marker. Let's say that we had this angle. Well, now cosine would be negative for this angle right here. Well, if that angle were negative, then we would rotate the other way. And if we rotate the other way, in orange, we would end up with this triangle over here, and still cosine would be negative. So whether I rotate positively or negatively, the x value stays the same negativity or positivity, and so these are exactly the same thing. And we could think this through for tangent as well. Tangent of a negative angle. Well, for that red triangle, tangent is y over x, so negative 3 over 4. So it still involves that y value, which we know as we rotate down versus up, the y value switches signs. So tangent of negative alpha is the same as negative tangent of alpha for the same reason it was for sine, because the y value changes its positivity or negativity. That's just 3, but you know, when you flip a fraction over, it doesn't change from positive to negative or vice versa. So this identity would be the same for cosecant, and this identity would be the same for secant, and this identity would be the same for cotangent. Okay, onward. Let's talk about Pythagorean identities. All right, so let's go back to our triangle spinning around a circle, right? So here's my circle, and here's my triangles. Let's say I have this triangle. All right. This is the x value. This is the y value. Together, they would be the x and the y value for this point. This is the radius of the circle. Well, as you know, Pythagoras was famous for a couple things. One thing that he was famous for is a squared plus b squared equals c squared, which is true on a right triangle. So in this example, x squared plus y squared would have to equal r squared. And that's an equation. And equations are pretty handy because I can do whatever I want as long as I do it to both sides. So I'm going to start by saying, well, what if I divide both sides by r squared? If I do that, then all of a sudden, you'd be like, hey, look, r squared divided by r squared, that's 1. And y over r, that looks familiar, that's sine. So sine squared, and x over r, that's cosine. So that means the cosine of any angle plus the sine of any angle, when you square them and add them together, you will always get 1, which is a nifty trick. You could manipulate this too, right? Like you could subtract sine from both sides and know that cosine squared equals 1 minus sine squared. That's handy to know that you can do that. Let's see here. If we divide it by r squared, what happens if we divide by x squared? Let's see here. X squared plus y squared equals r squared. I'm going to divide by x squared for no other reason than I have peculiar hobbies. And I can look at this and be like, x squared over x squared, that's 1. And y over x, that's tangent. So 1 plus the tangent squared of any angle is equal to r over x. Let's see, that's cosine flipped over, so that's secant. Secant squared. There's a second Pythagorean identity. And we divide it by r squared, we divide it by x squared, we can divide by y squared. If I have x squared plus y squared and it equals r squared, and I divide all of these by y squared, then now this is 1. And x over y is cotangent. So cotangent squared of an angle plus 1 equals r over y. Which one's that? It's cosecant, isn't it? Cosecant squared of an angle. And of course it's cotangent and cosecant because we've already used sine and cosine, and we've already used tangent and secant. So of course the last two remaining would be the ones we didn't use. So every time you see a square on a trig function, thinking Pythagorean identities is probably a good way to go, right? If I subtracted cotangent squared from both sides of this equation, I would get cosecant squared minus cotangent squared equals 1. So if I had cosecant squared minus cotangent squared in an expression, I could get rid of it and just replace it with 1, make my life a lot easier. What else do we have? Wait, did we do all of them? 1, 2, 3, 4, 5, 6. All right, that wasn't so bad. So how do we use these? That's the question. And the reason we're learning these is because as you get into calculus, you might have complicated trigonometric expressions that it would be useful to simplify to make your life better. And so here's my advice on simplifying. One is convert everything to sine and cosine. And the other is don't forget that monomials are a lot easier to deal with than polynomials. Like I can't, for example, if that were a cosine, I could not cancel those out because they're part of a polynomial. So whenever you can, tend towards monomials. So first I'm going to convert things to sine and cosine. Let's see here. My goal is to make this as simple as possible. So what I'm going to do is I'm going to think of the top of this fraction as like its own problem. And say that's 1 plus 1 over sine of x because cosecant and sine are reciprocals. And I will also see if I can deal with this. Now I'm not going to change the cosine because, you know, sine and cosine are useful. We're going to keep that the way it is. So I'll keep that cosine. But cotangent, I know from the quotient identities, is cosine over sine. Now I'm going to treat these like two separate problems. If monomials are more useful, then I'm going to take this and I'm going to look at that and say, I'm going to add those together to make it one number. And the same thing with the bottom of the fraction. So to do that, I would need, of course, a common denominator. So I am going to change this red expression to sine x over sine x, because that's equal to 1, plus 1 over sine x. Then, I'm going to change the blue one. It just shot up to them. I'm going to change the blue one here to, let's see here, I would need a common denominator for that. So I would have to multiply this side by sine x over sine x. Check it out. All right, now we have fractions we can add together. So I will add these fractions together. I will say that's sine x plus 1 over sine x. And cosine x sine x plus cosine x over sine x. Now you might think to yourself at this point, Nucci, you're insane because that is way more complicated than what we started with. And you're right. But you know what this is like? This is like cleaning your room. Like when you clean your room, it gets way messier before it gets cleaner, right? And then all of a sudden it snaps into shape. This is the same sort of idea. So let's see here. If I were to take a fraction and divide it by a fraction, I would have to take the bottom and flip it and multiply it. And so this I could think of as multiplying sine x over cosine x sine x plus cosine x. benefit of that is that, look at this, sine x and sine x cancel out. They're monomials, so you can cancel them out. So if I take this and write it out now, I have sine x plus 1 over cosine x sine x plus cosine x. Now, how to simplify this is not exactly intuitive, which is why I chose this example. But just remember that one of the tools in your tool bag is factoring. So if I take the bottom of this and I factor it, I could take out, see how there's a cosine x and a cosine x? I could factor that out and make this cosine x times sine x plus 1, and then lo and behold, Christmas miracle, sine x plus 1, sine x plus 1. So all of this boils down to 1 over cosine x. And that equals secant of x. And that's as simple as I can make it. Make them into sines and cosines, add fractions together, try to get monomials where you can, and then reduce. Remember that if you see a square, think Pythagorean identities. That is a simplification problem. That's a problem where you start with an expression and you are trying to make it as simple as possible. There are also problems you're going to encounter called verifications. Verifications are like proofs. Verifications are proofs. You're just trying to show that two things are equal, and you're writing down the steps that you are using to do so. If I went back here, and in a different, we're going to do this. If I went back here in a different color, I'll pick, I don't know, fluorescent green. I'm just going to write down what I did. What's the first thing I did? I used, to get from this to this, I used a reciprocal identity. To get from cotangent to cosine over sine, I used a quotient identity. Then I took these and I made common denominators. So I made a lowest common denominator to add fractions. Then I took this and I flipped it and multiplying. So that's just simplifying fractions. So I'm going to write simplifying fractions. And finally, one of the things I did was factor, so that can be one of my reasons. And then I reduced when I crossed out the sine x plus 1. And lastly, I went from 1 over cosine x to secant x. That's a reciprocal identity. So check it out. I've turned this simplification problem into a verification just by writing down what I did along the way. And that's all you got to do. So check it out. If we're going to take this, now this, they're telling you the answer from the beginning. They're saying this equals that. Prove it. So all you have to do is pick one side or both sides and manipulate them using algebra and using the identities until they're the same, and write down your steps along the way. I mean, if it's me, I'm going to look at this and I'm going to work with that one. And I'm going to work with that one because I already know, like, I can add fractions, right? So I'm going to take this, I'm going to multiply this one by 1 plus sine of x. And I'm going to multiply this one by 1 minus sine of x. I'm doing that to make a common denominator so that I can put these fractions together. So, what's my reason for that? Yeah, it's simple. I'm making a lowest common denominator. Okay, so let's do that. So I'm going to take this. Now I have 1 plus sine of x minus 1 minus sine of x over 1 plus sine of x times 1 minus sine of x. great question at this part. Can I cancel out these 1 minus sine of x's? The answer is no, because the top is a polynomial. The bottom is not a polynomial. It's one thing times another. So it's factored. You can only cancel out factors. But I can't cancel that out because it's part of a polynomial. What I can do, though, is I can distribute. And simplify the top. Okay, just going to do that. Sine x, so this would be 1 plus sine x. Let me use a different marker. Oh boy. There we go. We're going to use 1 plus sine x minus 1 plus sine x over, if I distribute these out, this is the difference of two squares, that. And 1 minus 1. Okay. So, what do I have so far? I'm trying to make this into that. I'm going to need a 2 at some point. Luckily, I think I have one. I have one because sine x and sine x is 2 sine x. But also, using a Pythagorean identity, if I go to the Pythagorean identities for a second, and I look at this, cosine squared plus sine squared equals 1. If I were to take that, and I were to cosine squared plus sine squared equals 1, and I were to subtract sine squared from both sides, then what I would get is cosine squared equals 1 minus sine squared. If cosine squared equals 1 minus sine squared, then I can take this 1 minus sine squared and turn it into a cosine squared. So I'm going to take this and turn it into a cosine squared. And the reason I'm doing that is because that's a Pythagorean identity. Then I can think of this as 2 times the sine of x over cosine x, because that's what a square means. And I can take sine of x, cosine x, this part, and I can turn that into tangent. Why am I doing that? Because that is a quotient identity. And I can take this 1 over cosine x, and I can turn that into secant x. Why am I doing that? Because that is a reciprocal identity. And oh, by the way, that 2 is still there. I have proven that what I started with over here equals 2 tan secant. 2 tan secant. I've proven it, I've written out each step, and that's how a verification works.